Okay, good morning, everybody. Welcome to this tutorial T3 on BATched Code Theory and Practice. My name is Raymond Yeung. I'm from the Chinese University of Hong Kong, and I'm the first speaker of this tutorial in the sense that I'm the one who speak first. And Shenghao Yang, my collaborator, who is with the Chinese University of Hong Kong, the Shenzhen campus, is the second speaker. But in fact, Shenghao is the first author of this work, meaning that he's the main contributor. Okay, all this work started in around 2010. Shenghao was my former PhD student who graduated in 2009, right? And then he worked 1 year as a postdoc at University of Waterloo with Professor Shenghao, with Professor Anhui Yang. And then he came back and worked in the Institute of Network Coding as a postdoc, and that was the time when we started this work. So throughout the last 6 or 7 years, we have developed a rather comprehensive theory, and also that we have done quite a bit of implementation. So at the end of this tutorial, Shenghao and his student will do a live demo on what we have done so far. And so I'm going to give the first part of this talk, and which is more the introductory part. Okay. All right, we start with some preliminaries. Here we don't assume that the audience here know a lot about network coding. So I'm going to give you a very quick overview of network coding. Okay, the history, it is a very brief history of network coding in the late 1990s, from the mid 1990s to the late 1990s. There was some work along the line of network coding. It was not exactly network coding yet. These, you can think of them as works that led to network coding. And these include multi-level diversity coding. And then there was one paper by myself and Zhen Zhang on satellite communication networks, which now can be viewed as a special case of multi-source network coding. And then in the year 2000, there was the paper by Auswader, Chai Li, and myself. And in that paper, we presented the butterfly network, which showed that network coding can do better than routing in a general situation. And then we also proved the max-flow min-cut theorem for network coding, which I will mention very briefly in a moment. And then in 2003, people were looking at linear network coding. First, there was the work by Li Yeung and Tsai, and then the work by Kurt and Madat, and these were independent work. And then 2005 to 2006, people started to look into constructions of network coding. And since 2006, there have been many different ramifications of network coding. These include network error correction coding, and also for secure network coding, physical layer network coding, subspace network coding, coding for distributed storage along the line of regeneration code and things like that, and coder caching, and so on and so forth. Okay, here's a quick example of network coding. In fact, this is an example of linear network coding. Suppose we have 2 bits x1 and x2 generated at source node S, and we have to multicast these 2 bits to 2 signals T1 and T2. Okay, the usual way to think of the problem is that, okay, we have 2 bits to transmit. So what we do is that we transmit x1 to the left, and then we make 2 copies. One copy goes down here, and another copy goes down here. Now, likewise, we send x2 to the right, and at this node B, we make 2 copies. One copy goes here, and the other copy goes here. Now, in this model, we assume that on each channel, you can transmit only 1 bit at a time. Okay. Now, the situation here is that we have 2 bits x1 and x2 entering the node C, but there's only 1 output link. So what are we going to do? Okay, if you let x1 through, then x1 can go this way and then reach T2. If you let x2 go through, x2 can go down here, and then it can go to the left and reach T1. However, as I said, you cannot let 2 bits go through simultaneously. So if you stick with the usual store and forward paradigm or routing paradigm, it's not going to work. However, if you allow a very small coding inside the network, in this case, we only need to take the exclusive OR of x1 and x2, or binary addition, if you like. And now this single bit goes here, and then you make 2 copies, one to the left and one to the right. Okay. Now this node T1, upon receiving x1 and x1 plus x2, which essentially tells you whether x1 is equal to x2 or not, because in binary addition, 0 plus 0 is equal to 0, and 1 plus 1 is equal to 0. Okay. If the 2 bits are not the same, namely you add 0 to 1 and 1 to 0, the sum is equal to 1. So it means that whenever the sum is equal to 0, it means that the 2 bits are the same. Whenever the sum is equal to 1, the 2 bits are not the same. Now here T1, upon knowing x1 and knowing the additional information, whether x2 is equal to x1 or not, then it can figure out x2. Now if x2 is equal to x1, then you know, upon knowing x1, you also know x2. If x2 is not equal to x1, then it must be the other value, because a bit has only 2 values. Okay? So that's the main idea. Likewise, for this node T2, upon receiving x2 and x1 plus x2, it would be able to decode x1. Okay, now, and then in 2003, 2 papers were published. The first paper by Yeung and Shenghao, the other paper by Curtin and Medard. These were independent work. And both papers proved that the capacity of single-source multicast network can be achieved by linear network coding. And this example is actually the simplest example of linear network coding, okay? Because here we are operating in the binary field. Okay? Now, not only that, here it means for achieving the capacity of single-source multicast means that the maximum min-cut bound is achieved. For this, I would like to use the same example to illustrate the point. Now, at the source node S here, if you consider the maximum flow from S to T1, because there are 2 independent paths, one go this way and the other one goes this way, so the max flow from S to T1 is equal to 2. Okay? Likewise, by symmetry, from the max flow from S to T2 is equal to 2. Now, if we just do unicast from S to T1, then we can simply route the bit x1 through this path and route the bit x2 from this path. Okay? Then T1 will be able to receive 2 bits. Similarly, if you want to unicast from S to T2, you can take this path to route x2, and then you can take this path to route x1. Okay? So if you talk about only unicast, then the receiver can always achieve the maximum min-cut bound. However, if you talk about multicast, we have seen that with routing, you would not be able to achieve the rate 2 simultaneously. Whereas if you employ network coding, then both receiver would be able to receive 2 symbols simultaneously. So what we learned from the main idea of the maximum min-cut bound is that if for a particular node, receiving node, there's a sufficient amount of max flow, then no matter whether there are another 1,000 receivers receiving the same information, my node would be able to receive the symbol, receive the information at rate equal to the max flow. Okay, that's the main idea of the maximum min-cut bound. Okay, so I only care about the whether I have enough max flow or not. I don't care whether other people are also receiving. Okay, so this point is very important, and we are going to make use of this in a moment. Okay, so in 2003 we knew that linear network coding can achieve the capacity of a single-source multicast network. And then 1 or 2 years later, people got interested in the construction of linear network codes, or efficient construction of network codes. In this paper by Jaggi-Sanders et al., they proposed an algorithm, now known as the Jaggi-Sanders algorithm, which can construct optimal linear network codes with in polynomial time, given that the network topology is known. Okay? And then there was a paper by Tracy Ho and her collaborators in 2003. The journal paper was published in 2006. And they talk about random linear network coding, namely that the coding coefficient at each node is being picked randomly without making any regard to the topology of the network. Okay? This is a distributed algorithm because by performing a random choice of the coding coefficient, you don't have to know anything about your neighbors or anything else in the network. Okay? And it turns out that with random linear network coding, even without network topology information, with very high probability, you would be able to achieve the maximum mean cut bound. Okay? I'm going to get into this in a moment. One thing to point out is that the gain of network coding over routing can be arbitrarily large, meaning that there could be examples you can construct such that network coding gain is much, much larger than routing. Okay? And for general transmission, with possibly more than one source node, however, linear network coding is not always sufficient. There are examples with multiple sources that even for unicast to different points in the network, it turns out that you need to use nonlinear codes. But for this tutorial, we will not talk about multi-source network coding. Okay. Now, in this talk, we will focus on networks with packet loss. So we are looking at a problem like this. Okay? So we want to transmit a file with k packets. Now, in the first part of this tutorial, k is pretty much the only parameter that you need to pay attention to. Okay? So the file consists of k packets. You know, think of k as the size of the file, and the packets are named x1, x2 up to xk. And for example, for a 2 megabyte file, if each packet consists of 1 megabyte, then we are talking about k equals 2,000. Okay? And we have one single source node. Okay, not necessarily the butterfly network, it's just an illustration. The idea is that for these k packets or symbols, what we encode them into different packets, and then we send them along the channels through the network. Okay? So these, so they're the brown ones and the red ones. The red ones are those packets that are lost along the way during the transmission, okay, for different reasons. So these packets traverse the network, and eventually some of them survive. And okay, at each node you're free to do any recoding you like. Okay, so eventually some of these packets receive a T1, and based on the received packets, T1 would be able to decode the whole file, namely the source symbols x1, x2 up to xk, and likewise we require the same for every other receiving nodes. Okay, so in this model we talk about one or possibly multiple destination nodes, but we stick with the assumption that there's only one source node, and there is non-negligible packet loss rate on each link. Okay, so we are looking for a practical solution which has low computational and storage costs, high transmission rate, and small protocol overhead. Okay? So these are usual requirements for a good protocol. Okay, now multi-hop networks with packet loss have very vast application scenarios. One possible scenario is vehicular ad hoc networks. Okay, yeah. Different vehicles can talk to each other through other vehicles, and each link can induce packet loss. Another scenario is mobile ad hoc network. And nowadays, smart city is a very hot topic, and in smart cities, smart lamppost is a very important component. So what you can do with smart lampposts is that you can put sensors for reporting weather conditions, for reporting the air quality. You can also report real-time traffic conditions with a webcam. And you can also put a Wi-Fi or 5G base station on the lamppost. Okay? So in fact, for the upcoming 5G networks, I will also talk about this in a moment. Because the transmission is at very high frequency, it's very directional. As a result, the cell size are very small. Okay? And that's why people are talking about putting base station very close to each other, because the cells size are going to be very small. Okay? So naturally, the lamppost is a possible place that you can put a base station. Now, one issue, however, is that not all lampposts can be connected to the wireline network. Okay? It can happen that only on this street only the first lamppost is connected to the fiber network, whereas for the other lampposts you need to connect them through a multi-hop network. Okay? So this is one application scenario of multi-hop networks. And here's another scenario for multi-hop networks. And different companies have already made proposals for launching thousands of satellites to cover the whole world, okay, and providing internet service. And in such a scenario, these satellites, in principle, they can all talk to each other a few times before they send a signal down to Earth. Okay? So there's also one application scenario. And another application scenario is underwater acoustic network. And well, this is a very beautiful picture which shows that the sea is a very beautiful and calm place. But in terms of communication, it is actually a very volatile communication environment. I was told by experts in this area that no matter what coding scheme or modulation scheme that you use, that the packet loss rate got to be quite high. Okay? And it's actually very challenging to build a multi-hop network under the water. Okay? And the very reason why people consider using acoustic waves to communicate underwater is because radio frequency actually deteriorates very quickly. That's why it cannot be used underwater. Okay, so why multi-hop wireless networks? One important thing is that we all know that the Internet of Things is coming, and there are various predictions on how fast Internet of Things is going to grow, but they all point to one thing, that is that there will be zillions of Internet of Things devices, and as we know, there's more and more interference in licensed and unlicensed band radio, both in the 2.4 gigahertz and 5.5 gigahertz frequencies. And as I mentioned just a moment ago, for 5G and also for 5G and also for 802.11ad, we are using millimeter wave for transmission, and these are highly directional transmissions, and therefore we need naturally we need smaller and smaller cell sites. Okay? And also low power transmission is the trend for all wireless communications, be it IoT or cellular. Okay? And low power transmission and small cell and cellular networks actually go hand in hand with each other. Okay? And very often, if you have an Internet of Things device, you may not be able to connect to the wireline network directly. Rather, you need to go through some other IoT devices, and that's why you need a multi-hop network. Okay, and there are also some underserved domain, like what I've mentioned, underwater communication or in the underground communication. In rural areas or where countries that does not have enough infrastructure for internet access, you may need to build a wireless multi-hop networks to connect the rural areas with the internet. Okay, and also we could be applying multi-hop networks to space and communication, also and even outer space communication. Okay, now let's take a look at some existing solutions for dealing with packet loss. Okay, the primary method to deal with packet loss is actually retransmission. Okay, in the internet backbone, because the internet backbone is pretty much hooked up by fiber networks with very low packet loss. If there's any packet loss in the networks, most likely it is due to congestion. And if this congestion is due to the fact that you pump too much traffic into the network, and at some point, at certain intermediate nodes, there could be a buffer overflow where you lose the packets. This is the mechanism how packets are being lost in the internet backbone. And to deal with this, what you usually do is to do it by rate control using TCP, because as I mentioned, congestion is due to pumping too much traffic into the internet. So in order to fix the problem, you reduce the traffic you pump into the internet by rate control. Okay. Now, and then if there's any loss, it is recovered by retransmission. For example, at the transport layer or TCP, you have an ARQ mechanism for doing that. Okay. Now, for wireless communication, at the first hop or the last hop, okay, in the scenario of Wi-Fi or 4G, etc., packet loss is is generated in a totally different manner. Okay? Packet loss is generated mainly by noise, interference, shadowing, etc. And because this has nothing to do with injecting too much traffic into the internet, this kind of packet loss problem cannot be fixed by reducing the traffic injected into the internet, okay, into the network. It cannot be solved by rate control. And nevertheless, the traditional way of recovering packet losses is also by retransmission at the transport and link layers. And that's why there's some inefficiency incurred in such application scenarios. And in fact, this is what this tutorial is trying to address. Okay, also another thing is that for retransmission, we know very well that it is suboptimal for a multicast. Okay. The reason is that suppose we have one transmitter transmitting different packets to the receivers. If you use TBC kind of protocol, then among these all these receivers, the transmission would be held up by the weakest receivers, because for every packet, you have to make sure that it is being received by all the receivers. If they don't receive, you keep retransmitting until everybody receives a certain packet before you can move on. Okay? So if there are some weaker receivers, these weaker receivers will hold up everybody. Okay? This is the well-known problem of using retransmission in a scenario of multicast in a wireless environment. Okay, so let's take a look at the simplest multi-hop network with packet loss, namely a line network with n hops. So here S is the source node and T is the sink node. In between, we have n-1 so-called relay nodes. Okay, so the total number of hops is equal to n. And here we assume that each link has a packet loss rate equal to epsilon, where this packet loss rate is before retransmission. There's no retransmission assumed. Okay? Okay, when epsilon is equal to 0, which means that each link is a perfect link, then the network throughput is 1 packet per use. Okay? Now, when n is equal to 1, meaning that there are no relays in between, there's only one hop, the network throughput is 1 minus epsilon packet per use, whether you do it by retransmission or you do it by erasure coding, such as Resolvent code or fountain code. Now, this is from a result from the classical information theory, saying that for an erasure channel with erasure probability equal to epsilon, whether you use feedback or not, the capacity is still the same. Okay, this is the well-known result from classical information theory. Now, in general, we can have n greater than 1, okay, which means that there can be more than one hop, and epsilon greater than 0, which means that the packet loss may be non-negligible for each link. So what is going to happen? Okay, now if you apply forwarding at each of these intermediate nodes, whether you use retransmission, end-to-end retransmission from S to T, or you use fountain code from S to T, as long as each intermediate node only perform the forwarding operation, I claim that the maximum rate that you can transmit information from S to T reliably is upper bounded by 1 minus epsilon to the power n. Okay? The reason is the following. Now, for each packet, because only forwarding is being done at each intermediate node, each packet must survive each of these n transmissions before it can reach T. Otherwise, it will be lost somewhere along the way and cannot be used for decoding whatsoever. Okay? Now, so after each hop, because a fraction of epsilon packets are lost, what remains is a fraction of 1 minus epsilon. So every time you go through one hop, you multiply by 1 minus epsilon. Okay? That's why the maximum rate is at most equal to 1 minus epsilon to the power n, which goes to 0 exponentially fast. Okay? It is exactly this reason why, with present technology, multi-hop network or wireless mesh network does not work very well. And because after a few hops, you get very, very few packets left. Okay? And that's the very reason why wireless mesh network has not been very popular. Now, in principle, or in theory, if you apply network coding, which I'll explain in a moment, you would be able to maintain a maximum rate equal to 1 minus epsilon, meaning that no matter how many hops you have, the end-to-end communication rate is as if there's only one hop between S and T. Okay, I'm going to explain to you why this is possible with network coding. Okay, now this picture actually in some way illustrates the situation. This is called a telephone game, or sometimes also known as Chinese whispers. I don't know why it is called Chinese whisper. So the idea is that in the first transmission, you transmit the word peace, and then the second, the girl didn't listen very clearly and thought this is the word bees, and the third person thought it's sneeze, and the fourth person says cheese, and the fifth person thought this is fleas. Okay, so the more hops that you go through, the more information loss you have. That's mainly what this illustration is about. Okay, so how are we going to reconcile the situation? So let's take a look at some possible methods that can reconcile the situation. So a possible method is called link by link retransmission. Okay, so for the n hops and between each pair of nodes, you do retransmission until every single packet is being received. Okay. Now, so for this implementation, unique link by link acknowledgements, okay, and which may or may not be available, and such a scheme would be optimal for unicast when acknowledgements are reliable and cost-free. Okay? However, in general, this may not be the case, and very often when the forward channel is noisy, the acknowledgement which are transmitted on the reverse channel is also quite noisy, and that's why the acknowledgement is when the forward channel is noisy, the reverse channel acknowledgement may not be reliable. Okay? And it may not even be available in some situation. For underwater communication, as I said, the channel is very noisy, so you cannot rely on the acknowledgement. And also for deep space communication, because there's a huge delay. Okay? There's a very huge distance between Earth and also the spacecraft. Okay? And it can take like maybe a year before the acknowledgement can come back. Okay? So it's essentially not useful. Okay? Now, one drawback for link-by-link retransmission, other than the unavailability of acknowledgement, is that you need to cache roughly square root k, the order of square root k packets at the intermediate nodes. Okay? This is something that can be obtained by calculation. Okay? So what k is, as I mentioned, is the size of the file that you're transmitting. So as long as the cache depends on the size of the file, it's not something very good from the engineering point of view, because when you design the system, you may not have any idea how large a file that you're going to transmit, and you don't know how large a buffer you need to put at the intermediate nodes. Okay? And it's also far from optimal for multicast, because as I explained, if you do retransmission, usually it causes a lot of problem. Okay. Another possibility is do it through link-by-link erasure coding. So for example, you have n hops, and for each hop, what you do is that from node number 1 to node number 2, you use one Founding code. Okay? And then at node number 2, you completely decode the Founding code, and then you re-encode it using another Founding code. So you're repeating the process, and by doing so, you would be able to maintain the rate equal to 1 minus epsilon, no matter how many hops that you go through. But the issues here are the large delay that is incurred, because at every node you have to wait until you can decode the whole file before you can recode. That's why delay accumulates along the way. So the more intermediate nodes you have, the more delay, end-to-end delay you would experience. And also, you basically have to cache the whole file at each of the intermediate nodes, and that's why the buffer size is O of k, okay, which is not something desirable. Whenever we see something, whenever we see k appearing, it's not good news. And also there's a high computational cost at the relays and also at the the destination nodes, and again, it's far from optimal for multicast. There is another approach. Instead of doing a complete decoding and then re-encoding at every intermediate node, there is an approach called Reek Re-Encoding, or sometimes known as a systematic re-encoding. So the idea is that at each intermediate node, from node 1 to node 2, I use one founding code. At node 2, I don't decode the founding code. Rather, I encode it using another founding code, which specifically a systematic founding code for the sake of efficiency. So every time you encode it using another layer of founding code, the main idea is that by doing so, you don't have to decode, so that you can save some computation at the intermediate node. But at the destination node, you have to pay the price because you have to decode many layers of founding codes, okay? And that causes a lot of computation at the destination node. That's why we say that this approach is nothing but to shift the decoding computation from the intermediate nodes to the destination nodes, okay? Okay, so I'd like to introduce random linear network coding. And as I mentioned, let's see. For a multicast network, linear network coding can achieve the capacity. In particular, it can be achieved, the capacity can be achieved by constructing the code randomly. That is, you pick the encoding coefficients randomly from a finite field, and with high probability it will work. Okay. Moreover, random linear network coding not only achieves the capacity of a fixed network, but with perfect communication links. But in the case that there are packet loss on the communication links, random linear network coding continues to achieve the capacity for a large range of such multicast networks. Okay? So I'll refer you to these references if you're interested in the details. Okay, so this is a baseline random linear network coding scheme, actually first proposed in this paper by these two researchers from Microsoft Research at Cambridge in 2005. So, so the idea is that you have the top layer is the layer of source symbols. Okay, so what you do is that to form the second layer is the layer of coded symbols. To form a coded symbol, what you do is that you take a random linear combination of all the source symbols. Okay, and to form the second coded symbols, you take a different random linear combination. Okay, so every time you take a different random linear combination, but you take the random linear combination of all the source symbols. Okay? You don't miss any single one of them. So you transmit these coded symbols through the network. Okay? And some of these changes color from green to red, meaning that the packet is lost. Okay? So for those that are lost, they are not seen at the relay node. And the relay node just do another layer of recoding. Okay? So whatever you have on hand, you just take a random linear combination and then you send out the coded symbols. For example, at this point, when the time is equal to 3, you already have 3 symbols received. And then what you do is that you take the random linear combination of these 3 symbols and to form another coded symbols, and you send all on the output link. Okay? For those red symbols, you don't see them anyway. Okay, now here we assume that each packet has T symbols taken from a finite field of size Q. Now T symbols, T is a constant. Okay? In our discussion, each packet has T symbols where T is a constant. And the finite field size Q is also a constant. Okay, here's an explanation why random linear network coding can do the job. Okay, so maybe we should go back to this network. Okay, consider the case that you have source node S is a signal T, and then one relay node in between. Okay? So here we have 3 rows, where the first row represented the source node S, the bottom node represents the signal T, and the middle row represents the relay node, okay? Where the horizontal axis is a time axis. Okay? So this represents the source node as at T equals 0, T equals 1, T equals 2, so on and so forth. Okay? Now here in this graph, well, I call this a time expanded graph. Okay? Now in this graph, there are 2 types of edges. There's some edges making an angle. Okay? So here, this edge represents the transmission from the source node to the relay node, and the time delay is equal to 1. Okay? And the capacity of this link is equal to 1, meaning that you can send one symbol through. Okay? So likewise, you can send one symbol from here to here, from here to here, so on and so forth. But once in a while, let's say but the packet loss is equal to 20%. So on average, 20% of these packets are lost. And this corresponds to putting it across on edge, which means that the link is broken. Okay? Now, likewise, we can send packets from the relay to the sync node at different time slots. Okay? Again, there's some crosses corresponding to packet loss. Okay? Now, there are also a kind of edges which we mark in black, which goes horizontally with capacity infinity. Now, this edge represents the memory from the past. Okay, you pass what you have received from the last time slot to the present time slot. Okay, and then the capacity is equal to infinity because you can pass everything you have received so far to the next time slot. Okay. Now, imagine that these are water pipes. Okay, so you have water pipes with capacity infinity going horizontally. Now this is a source node, and because so for those nodes, for those edges with the cross, you imagine that the water pipe is blocked. Okay, so because 80% of because 80% of these water pipes are still working, you can press water down from the top layer to the middle layer at rate equal to 0.8. Okay, that's clear, right? Because 80% of the pipes are working. Now, likewise, because there are 80% of the pipes from the second layer to the third layer are working, you can press water down from the second layer to the third layer at rate equal to 0.8. So that's also clear. Now, the question is whether you can press water down from the top layer to the bottom layer at rate equal to 0.8. Now, the answer turns out to be yes, because of the existence of these thick pipes going horizontally. Because once you press down from the top layer to the middle layer, the water will find their way horizontally and then go down to the bottom layer at rate equal to 0.8. Okay, intuitively, this is clear. Okay, in fact, it can be proved mathematically. That's the max flow of a node at the bottom layer between the source node and such a node grows at a rate equal to 0.8. Okay. So now, what has this to do with random linear network coding? Now, you look at this graph more carefully. Let's say we examine a particular node here, okay, at a certain time instant. Now, there are 2 incoming edges. One is from the left, which are the memory from the past, and the other one is from the top, which is a newly arrived packet. Okay. And what you do is that you perform random linear network coding here, and then that is you take a mixture of everything in the past, and then with a new coming packet, and then you send out another packet. Okay. If you do random linear network coding on this graph, then you are exactly mimicking what is shown in this picture. Okay, and that's why for random linear network coding, as long as we have enough max flow, we would be able to pump information through at that rate. And we have shown that the maximum flow from the source node here to a sync node at the bottom grows with time at rate equal to 0.8. And that's why random linear network coding would do the job. Okay, however, there's some complexity issue with this implementation of random linear network coding. First of all, to generate one packet in encoding and recoding, we need all of KT operations, where T is the number of packets in number of symbols in a packet, which is constant, but K is the number of packets in the file, which represents the size of the file. That is, the encoding and also recoding complexity grows linear per packet, grows linear with the file size, which is bad news. Okay? Now, for decoding, the complexity is even higher. To decode one packet, on the average, the complexity is of order O of KT plus K squared. Okay? Basically, it's K squared. Right? So whenever you see K, that's not good news. Okay. Also, we are concerned about the storage at the intermediate nodes. For random linear network coding, you basically have to store the whole file at the intermediate nodes, and that's why it is order of K. And the coefficient vector overhead is also something that we need to consider. I'll explain this in the next slide. Okay, what's the coefficient overhead? Now, we let B be the matrix formed by the K input packets. Okay, so each row is consists of K packets, and so this is you consider this block as the file that you try to transmit. Here we are not transmitting only one file, but we are transmitting multiple files. Okay, so this is the block of information that you try to transmit, and then when you go through the network, it goes through a certain linear transformation induced by linear network coding, and that's captured by a matrix H. Okay? At the end, you get a block of symbols Y. Now, if H is invertible, upon knowing if H is known and also invertible, then upon knowing Y, you would be able to recover the matrix B, which consists of the source symbols. Okay? However, in general, H is not known because you perform random linear network coding within the network. You don't know what random coefficient that has been picked. Okay? Now, in order to solve this problem, what you can do is that you, in addition to transmitting this block of data B, you transmit a identity matrix. Okay? By sending the identity matrix through, okay, B times H is equal to Y, but the identity matrix times H is equal to H. Okay? So by doing this, you learn the transfer matrix induced by linear network coding within the network, and as a result, you would be able to recover H, and by inverting H, and also knowing Y, you would be able to decode B. Okay? Now, but this is the so-called coefficient vector. It doesn't come for free, and the overhead induced by this coefficient vector is given by T over T plus K. Okay? T is the number of symbols in a packet, and K is the file size. So when T is much larger than K, then this is essentially equal to 1, which means that you're using the code repeatedly with the same with the same transfer matrix. Okay. So although asymptotically you can make this coding vector overhead approaching 0, but in reality it is not something that you can always neglect. Okay. So there are different approaches along this line, and one approach is to I've mentioned some issues for those schemes that I have just talked about, and in order to alleviate the problems, there have been different approaches being taken. One approach is to modify foreign codes for network coding. So well, as I mentioned, the complexity of random linear network coding is high, precisely because at the source node you perform very dense coding. Okay? For this coding, previously we have a picture like this. So you see a lot of edges here, so there's a very dense coding. it corresponds to a matrix which is very dense. Okay? Now, and a dense matrix we know causes computational complexity. To alleviate the problem, one approach is to make this coding sparse, and a natural candidate is to use, for example, function code. Right? However, at the intermediate nodes, the function code starts out to be a sparse code, but at the intermediate node you do random linear network coding, and that would change the sparsity of the function code. And at the end, you would have to invert a dense matrix. There are certain techniques that you can do at the intermediate nodes instead of doing a complete randomization. You do some more clever or more restrictive randomization that would help. Reduce the denseness of the coding matrix at the end. But these are some rather ad hoc methods and does not apply in general. Okay, another approach is the following. Because for random linear network coding, the complexity grows with k. Okay? So when k is large, then you have a problem. So one approach is that you break the problem into smaller problems. That is, you use a small k, but you repeat the process. Okay? Now, by doing so, there are some issues. Now, first of all, let me introduce this symbol m, which stands for the size of each chunk. We call this a chunk. We chop up the file into chunks, and then we process them chunk by chunk. Now, for the coefficient overhead, it is given by m symbols per packet, and recoding computational cost is O of m times k. Okay? Still, by doing this, the recoding computation is still proportional per packet is still proportional to k. Okay? Now, in order for the efficiency to be high, okay, or the complexity is low, each chunk must be sufficiently small. For example, less than 100. However, if you use a small chunk, then you don't take advantage of network coding in full-fledged. Right? And so it is going to reduce the information theoretic capacity of the system. Now, however, okay, so I mentioned some issues here, but the main issue actually is the issue of scheduling the chunks. So you divide the files into chunks, and then you process this chunk one by one. Okay. The question is, how are you going to transmit the chunks? One approach is that you transmit the chunks sequentially, but then you'll face the same TCP problem. Okay. In the case of Multicast, if there's some weak receivers, then you hold up the whole process. Okay. And if you use random scheduling, then you which means that I have a bunch of chunks. I process them one by one, and then I decide to transmit any one of them randomly. With a certain problem, I just pick one and I transmit it randomly. The issue here is that suppose at the receiving end, 90% of the chunks are already received. Then if you randomly pick a chunk to transmit, then with probability 0.9, you will transmit a chunk redundantly. Okay? So this is also some issues that cannot be easily solved. Okay, so here we talk about our solution called BATched code. Okay, well, as I mentioned, during the last 6 or 7 years, we have developed quite a comprehensive theory for BATched code, and these results are summarized in a monograph that we published last year, namely this one. If you're interested during the break, you can come over and take a look. And so this is for BATched code, we introduced something called an inner code, outer code framework. Okay, so this framework works like this. So as I mentioned, as before, we use this first row to denote the source symbols. And the second row is the coded symbols, but these coded symbols are now divided into grouped into chunks. In this case, each chunk has size equal to 3. Okay? So Well, actually, in our terminology, we call it a batch, but a batch is not too much different from a chunk. Sometimes people call it a group, a class, or segment, whatever. Okay, there are different names for that, but we call this a batch. Right? Now, so in order to generate the first symbol in the first batch, what you do is that you take a certain number of symbols, and then you take a random linear combination. To generate the second symbol in the first batch, you stick with the same subset of symbols, and then you take a different random linear combination. In this particular example, to generate the first batch, we use source symbol number 1, number 2, number 5, and number 7. Okay, 1, 2, 5, and 7. Okay, and then you take 3 different random linear combinations to form the first batch. Okay. To form the second batch, through some mechanism, you pick another subset of symbols, and every time you take a different random linear combinations. Okay. So these symbols are being sent to the next relay node, and at the next relay node, this recoding is being done, but it's being done only within the same batch. Okay. For example, the first batch, here it consists of 3 symbols. We take 2 different linear combinations and from these 3 symbols. Okay. For the second batch, we may take 3 different linear combinations. For the fourth batch, we take from 3 symbols, we actually can generate 4 coded symbols by taking 4 different random linear combinations. So it does not matter whether you generate the same number of symbols or not when you do the recoding. Okay. So this part is called the inner code, which occurs within the network, okay, at every intermediate node. Whereas the outer code is this part here, which occurs at the source node. Okay. Now the outer code is actually a matrix generalization of foreign code. It could be an LT code or a Raptor code. The LT code is the one originally proposed by Luby, and Raptor code is subsequently proposed by Shokolahi. Okay? So to be more specific, let's see. Okay, to be more specific, this is what we do. To generate the first batch, what you do is that you draw something called a degree from a degree distribution. In this example, the degree being drawn is equal to 4, which means that we are going to take 4 symbols from the set of all source symbols, and we randomly pick 4, and it turns out to be 1, 2, 5, and 7. Okay, and then so you take different random linear combinations of these 4 symbols to finish the first batch. To start the second batch, you take a different degree from the degree distribution, and then you start over again. Okay. Okay. Now for this BATched code operation, the complexity is the following. For the outer code encoding, the complexity is O of MT per packet. Now here's the difference. You don't see the symbol K appearing, where K represents the size of the file. Whenever you see K, it's not good news. Whenever you don't see K, then it's good news. Okay? So it's constant complexity per packet, no matter how large the file is. Okay? For to outer code encoding, for the inner code recoding, again the complexity is O of MT per packet. It does not depend on the file size. And for the belief propagation decoding, which I'll explain in a moment, the complexity is O of M squared plus M times T per packet, where M is the size of a batch, which in our example is equal to 3, okay, to start with. And again, K does not appear, which means that for decoding, it is a constant complexity per packet, regardless of the file size. Okay. Okay. Now, originally, we came up with this inner code, outer code framework to describe BATched code, but it turns out that this framework is also useful for describing certain codes that are already in the literature. They can be casted into this framework, and these include some work on overlap chunk codes using repetition codes as the outer code, and also generalized LDPC code as the outer code. Okay. Just want to mention this. Now for the encoding, I think I jumped the gun a little bit. Now, for each batch, you obtain a degree D by sampling a certain degree distribution psi, okay, like this. And then after you do the encoding, these symbols can be just sent out sequentially. And here xi denotes the ith batch. For example, x1 is equal to, in this case, the three symbols for source symbol forming x1 are B1, B3, and B4. Okay, so you form a vector B1, B3, B4 like this. And then you multiply this by a random generator matrix where the entries are random symbols taken from the finite field. And if you denote this row vector by capital B1, then you get x1 is equal to B1 times G1. And x2 is equal to B2 times G2, so on and so forth, where B2 is equal, in this case, is equal to B1, B2, B4, and B5. Okay. So in general, we have xi is equal to bi times gi. Okay. So this is how the autocode encoding is being done. Okay, okay, so when m is equal to 1, okay, that is the batch size is exactly equal to 1, then it reduces to the classical LT code, okay, which is a form of finite code. Okay, now for the analysis, we assume that this generated matrix GI is a totally random matrix. Okay, this facilitates performance analysis. But for implementation, we don't really need to use truly random linear generated matrix. Rather, we can implement this using a pseudo random number generator. Okay. So you can, basically the idea is that you use a pseudo number generator to generate such a coding scheme. Okay? And then you just transmit the pseudo number generator to the receiver, and the receiver, using exactly the same procedure, would be able to reconstruct this coding scheme. Okay? So this is how you can convey the coding scheme over by using a pseudo number generator, random number. Okay, so these are x1, x2, so on and so forth are the batches generated by the autocode at the source node. And so I would like to talk about the degree, okay? So we let psi be the degree distribution, and psi bar be the expected degree, and the expected degree is as usual given by summation d, d from 1 up to whatever, okay. Psi sub d is the probability that the degree is equal to d, okay. And then suppose that the generator matrices are dense, and we can generate a batch of degree d using this number of operations, this number of finite field operations. Okay, and the average complexity of generating a batch is given by this, and the average complexity of generating a coded packet is this. Okay, so you just divide. Here is psi times m times t. This is for generating a batch. To generate a coded packet on average, you just divide this by m, and so this is given by psi bar times t, which does not depend on the file size. Okay, so maybe I'll skip this issue here. All right, so now the batches x1, x2, x3, so on and so forth are generated by the source node, traverses through the network, and at each intermediate node, random linear network coding is performed, but only within the same batch. Okay, and then at the end you get y1, y2, y3 out from the network, where yi is equal to xi times hi, and hi is the transfer matrix that captures the random linear network coding operation within the network. Okay. Okay. Now okay, so we have seen that yi is equal to xi times hi, where xi is equal to bi times gi, where bi is the vector of the source symbols involved in forming the ith batch, and gi is a random generator matrix. So at the end, we have yi times xi times hi, which in turn is equal to bi times gi times hi. So the total, the overall linear transformation performed on bi is actually given by gi times hi. Okay. All right, so I would like to skip the details here. I just want to mention that for this batch transfer matrix hi, actually what only matters is the rank distribution of this matrix, but not the details of this matrix. Okay. Now this matrix is a matrix with all the entries being some random variables. Okay, because these are they capture the random linear encoding performed on the batch. So what I claim is that for the design of the code, which I would talk in a moment, you don't need to know the joint distribution of all these random variables. Rather, what really matters is the distribution of the rank given by this random matrix H. Okay. Okay, so let me repeat. The rank distribution of hi is sufficient for characterizing the inner code. Okay, so in terms of field sizes, there are two things that I would like to mention. Okay? The outer code and the inner code may use different field size. Okay? For example, the outer code may use a symbol from GFQ, okay? And which is a large field, whereas the inner code at the relay nodes use a subfield GFQM of G of Q. Okay? For example, you can use a large field for the outer code, but you use only a binary coefficient for the inner code, okay, for the mixing at the relay node. Okay? And using smaller fields for inner code reduces the recoding complexity and coefficient vector overhead. But this is going to reduce the information theoretic efficiency of the code, but sometimes when it comes to implementation, because you can now do things much faster on the processor, overall you may still gain. Okay? Okay, here's something about decoding. So, so the decoding is to, okay, yi is equal to bi times gi times hi, okay? So if we write all these equations all together, okay, then we can actually write it in this way, okay? So y1, y2 up to yn, and then we have this b formed by all the k input packets, and then g is basically, you put these gi's, random generator matrices together with adding 0 rows suitably, and then you have the b times this matrix g tilde times and then you put all these hi's as it's kind of like a block identity matrix, okay, like this. So we are to solve for the b's. Okay, upon receiving the y, we want to solve for the b, and the linear system has a unique solution only if k, which is the number of symbols, is less than or equal to the total rank of all the hi's. Okay? Because for you go through the matrix hi, the number of symbols that you can possibly decode is at most equal to the rank of the matrix. Okay. Okay, so there are two parameters that we are concerned about for Gaussian elimination decoding. The first one is the rate of the outer code, which is given by theta equals k times k divided by n. The k is the total number of symbols in the file, total number of packets in the file, okay? And n is the number of batches. So the rate of the outer code is equal to k divided by the total number of batches, okay? And we assume that for the sake of analysis, we assume that there exists an average transfer matrix rank, namely that if you let n goes to infinity, you take the average of all these rank of hi, it converges to some quantity h bar. Okay, so obviously the rate of the outer code must be upper bounded by the average transfer matrix rank. You cannot do it better than that. And the upper bound is achievable when you let psi k is equal to 1. That is, all the batches have a degree k, namely that is there's only one batch, okay, in the system. And this reduces to random linear encoding, and then you can solve the decoding linear system by Gaussian elimination accordingly. But this is not going to be computationally efficient, as I mentioned. If you use the baseline implementation of random linear encoding, you have to pay a lot for the decoding part. Okay. Now, instead of using Gaussian elimination, because of this inner code outer code structure, the inner code, you do random linear combination within the same batch. This does not change the structure of the outer code. That's why we would be able to use something called a matrix version of a belief propagation decoding. If you're familiar with belief propagation for Fountain code, you would find this a straightforward generalization. Okay? So recall that for the ith batch, the linear equation associated with it is equal to yi times gi times yi is equal to bi times gi times hi. So the linear transformation applied on bi is equal to gi times hi. Okay, so each associated with each batch is the matrix gi times hi. Okay, so we have a g1 h1, g2 h2, g3 h3, so on and so forth. So for every batch, you receive a certain set of equations. Okay, now in the classical belief propagation decoding, what you do is that you find a check node with degree equal to 1, and then you start propagating from there. So what it corresponds to is that you have many linear equations. You find one linear equation such that there's only one variable, and you solve that variable accordingly, and then you substitute that value into the other equations. Okay, this is what you do in belief propagation decoding. Now, for this case, what we propose is a matrix generalization of belief propagation decoding. So what we do is that we find a check node I with degree equal to the rank. For example, if the rank of G1 H1 is equal to 2 and the degree is equal to 2, which means that it depends only on two variables, B1 and B3, you can solve for B1 and B3 simultaneously. Because the rank is equal to 2, you can solve them simultaneously, and then you can substitute B1 and B3 into the other equations, and that's how you do the propagation. Okay, with this, the complexity is given by O of m squared times n plus tm n blah, 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 okay? The good news is that the k does not show up, okay, in this decoding complexity per packet, okay? Now, to recover all the k input packets using n batches with probability at least equal to 1 minus 1 over k to the power c, so you can think of this as a probability almost equal to 1, right? Asymptotically in some sense, okay? Now, it can be shown theoretically. Okay, now let me repeat, okay? Now, we want to recover all the k input symbols using n batches, okay, with high probability, okay? Now, it can be shown theoretically that in order to achieve this, the average degree, okay, recall that this is the degree, okay? Okay, this is the degree. The degree of the first batch is equal to 3, okay? Now, the higher the degree, the more computation you need to perform, okay? So we want a small average degree in order to make the code efficient, the encoding part efficient. So it turns out that yes, we want to use a small average degree, but there's a fundamental limit. It can be shown theoretically that the average degree must be lower bounded by some constant C prime times log of K. It cannot be too small. If the average degree is too small, then you will not be able to recover all the K input symbols with high probability, right? Now for LT code, Luby actually found a degree distribution which is of this order, log K order, okay? Right. So this is already the best that you can do. But log K is not something that that's most desirable, because the decoding complexity is proportional to log of the size of the file, which is not good, okay? We hope to have a decoding complexity which is constant per packet, regardless of size of the file, okay? Now, this fundamental problem was solved by the use of replicas invented by Amin Sakralahi. And so what he observed was that instead of decoding all the K symbols, if you only require yourself to decode a fraction eta of the K symbols, then you actually can be able to make the average degree independent of the size of the file, okay? It only depends on M. In this case, I mean, they were talking about M equals 1, okay, at that time. And this is just something that depends on eta, okay? So you're not going to decode all the K symbols, but you decode a large fraction of the K symbols. So how to recover the remaining input packets? You can only decode, let's say, 95% of the source symbols. So the fix is that you do it by applying a precode. Okay, a precode is nothing but a high rate erasure correction code. So you apply a high rate erasure correction code to start with, and which requires you only to decode 95% of the source files symbols, and then from that, by decoding the erasure correction code, you would be able to decode all the source symbols. Okay, here are some design principles that I would like to talk about. Now I mentioned that for the Unicode, the operation is actually captured only by the distribution of the rank of the transfer matrix, okay? But not by the details of the transfer matrix. Okay? In fact, the inner code hides many details of network operations from the outer code. Okay? So all these effects, packet loss, recoding methods, network topology, bandwidth, latency, all these effects are reflected only in the inner code. Okay? The design of the inner code does not need the details of the outer code except for the batch size and the and field size. And the rank distribution of the batch transfer matrix, as I mentioned, is a sufficient statistics for the outer code design. There's something included in the slides, but in the interest of time, I would not get into the details of that. Okay, so the design coding rate theta is equal to K over N. This is the coding rate of the outer code. And the average rank is given by this. Okay, we assume that it will converge. And the coding overhead is equal to the H bar minus theta. Now, H bar is the fundamental rate of information rate that you can convey reliably through the code, okay? And it cannot be larger than the average rank of the transfer matrix, okay? Whereas the theta is the actual coding rate of the code. So the coding overhead is equal to H bar minus theta. This is the gap between the fundamental upper limit and the actual code rate of the outer code. And the communication cost of batch I is given by Ci. This is actually the size of the ith batch. Okay, you don't have to use equal size, okay, in principle. And the average communication cost is given by 1 over n times the sum of all the CIs. Okay? So this is the average size of each batch. And the communication efficiency is given by the following. K is the number of packets that you can convey using the code divided by the number, summation ICI is the total number of coded symbols. Okay? And so this is equal to K, theta divided by C bar, and you plug in this equation, you get H bar minus the coding overhead divided by C bar. We want the coding overhead to be as small as possible from the design point of view. Okay, the primary design goals are the following. For the outer code, we want to achieve a this guy, CO, coding overhead, to be as small as possible. Namely, that's the rate of the outer code is very close to the average rank of the transfer matrix. And for the inner code, we want to maximize the expected transfer matrix ranks normalized by the communication cost. Okay? We try to maximize the average rank, okay, normalized by the average number of symbols that you for each batch. Okay. Okay, so we are getting into section 3, and I'll let Shenghao take over.
Okay, I may start a little bit. So the second part of this tutorial, we will discuss the details of how to design the inner code and also the outer code. We will begin with the design of the inner code. This is also called the recoding. Recoding is how the intermediate node further encode the batches. So this is basically about network coding. So the batch code is a combination of fountain code and network coding. But it's not simple combinations. For both network coding and fountain codes, we will introduce some new idea, new results to make the whole code works better. I will start with the recoding design. The input, the parameter we fix is m. Fix the batch size. We fix the recoding field size. These two we will know from other experience. The variable we will tune for recoding design is 3 parts. The first is how to generate the recoded packets. The second is how many packets to transmit for a batch. The third is how to transmit the batches. Okay, 3 things. Yeah, how to generate recoded packets, how many to generate, then how to transmit, right? These 3 parts. And the overall goal is to maximize the expected rank normalized by the communication cost. Because without normalize the communication cost, you can make the expected rank m, right? And it's upper bounded by m because we have batch size m. So that we must normalize by the communication cost. This is also maximize the communication efficiency when the coding overhead, CO, is 0. Yeah, we will show later that we actually can design outer code so that the CO can be very close to 0. We will first use an example in LAN network to illustrate this recoding. Suppose we have a batch of size 4. The source node apply recoding. You've noticed that the source node apply outer code generate the batches, but the source node also apply recoding. Yeah, it's very important. Actually, the source node also apply recoding. It generates file packets. In the our notation, we use mtutor to denote the number of recorded packets transmitted by a node. In this case, it's 5. We transmit these 5 packets. This denotes a packet loss. And in the intermediate node, this is one of the recoding node. It receives 4 packets of the batch. Yeah, I'm talking about only one batch here. It receives 4 packets of a batch. Then it apply recoding, generate file packets. In this case, I use random linear coding. Random linear combination assume that each package is a linear combination of all the 4 packets it received. And it also generates file packets. This is denoted by mtutor. And the file packets are transmitted, and one of them is lost. Yeah. We can add more intermediate nodes, but now I use 3. Yeah, remember that this mtutor may not be same as M. Capital M is batch size. Mtutor is the number of packets you transmitted for a batch. They can be different. Some notations to model this recoding process. I introduced a matrix called phi0. Phi0 is the matrix, in this case, it's a totally random matrix of dimension 4 by 5. And phi1 is also a totally random matrix of the same dimension. Suppose if we have 2 packet loss here in this link, then this node only receives 3 packets, then this phi1 will be 3 by 5 matrix. And I also use this matrix E1 and E2 to model the packet loss. This E is a diagonal matrix. Diagonal matrix, and the diagonal component can be either 1 or 0. If it's 1, means that packet is correctly received, it's 0 packet loss. Then the overall network transmission can be modeled by the multiplication of these matrices. You see, I can define that at beginning, the H0 is an identity matrix. Then Hi is equal to Hi minus 1 multiplied with phi I minus 1 EI. I can do this so on and so forth to get the batch transfer matrix of all the nodes. But what do we care about is the rank, right? We know that we don't really want to know the exactly distribution of H. We only care about the rank distribution. Then the rank distribution of this H0, H1, so on and so forth forms a Markov chain. And like pi I is the rank distribution of Hi, then we can get this formula. This pi I equals to pi 0 multiplied p to the power I. P is the probability transition matrix of this Markov chain. Yeah, here I make a very ideal assumption so that this Markov chain is homogeneous. Then we use pi to the p to the power I. In general, yeah, it may not be homogeneous, but we can also derive pi I similarly. It would depend on mtutor, recoding method, packet loss pattern, so on and so forth. Okay. Yeah, we have the formula. We can do the calculation. We can calculate what the expected rank for different network lengths. This is an illustration. Now I call it baseline recoding. Baseline recoding means that mtutor equals to m. I don't generate more packets to transmit, just the same, and as my batch size. And we use random linear recoding, and packet loss is 20%. We have a lot of lines. Basically, we use different batch size, M, and different field size. Here, we choose two field sizes, recoding field sizes. One is a larger one, 256. Another is a binary field. We see that one field size is very large, 64. It's very large in this site, but it's not a very large number. The performance of binary field and the larger field are very close. But when field size is small, let's look at m equal to 2. This blue curve, right? The batch size is small. Batch size is small. The difference is quite large. When m is 1, it becomes the fountain code or IoT code case. It's here, this black curve. Okay, this is an example. Now we will discuss the details about the recoding methods. There are different methods we can use in generate recoded packets. This is the random linear recoding I just illustrated, but I did not show the latency. Actually, in the recoding node, to use all the received packet to generate a new packet, it must happen after you receive the last packet. So actually generate a latency here. So this latency will accumulate hop by hop. All the recoding node generated this latency, so this is not a good news. Also, the recoding complexity is high due to every packet you transmitted, you involve all the received packets. But in terms of the expected rank of your batch, that's good. Yeah, nearly optimal, especially when field size is large. To resolve the latency issue, we can use this causal recoding. Causal recoding means that you do recoding using the packets you have received. So when you only have one packet, you just transmit this packet. When you have two packets, you transmit the linear combinations of these two. Then in the search time slot, you don't receive anything, then you still use these two to generate a packet. So on and so forth. You don't have extra latency here. It's good. But you see that the rank may not be so good because you see these three packets here actually has only rank 2. One of them is redundant. So this packet is erased actually at the destination node. Even though it received 4 packets, actually the rank is at most 3. Yeah. So that means the rank is not good. The expected rank is low, especially when M is small. But we know that when M is very large, this tends to be optimal. But we don't want to use very large batch size. An even better approach is called systematic recoding. Because causal recoding still generates a lot of recorded packets. But we don't, right? This is the original batch we have. We can just transmit the original packets and add extra packets as the recorded packets. Systematic recoding. We don't just generate too much new packets. We transmit the packets we received directly, and after all the packets has been received, I just transmit one more as my recorded packets. This is called systematic recoding. You transmit what you received. Systematic recoding saves a lot of computation cost. And the expected rank, it's actually the best among the approach I introduced here. And it also has a very little extra latency. We can combine these two ideas of causal and systematic together. Because just now, in systematic recoding, this time slot I don't use. But why not use it, right? If there's no other data transmitted on the channel, I can also use this link. It may be helpful. So this is a combination of causal and systematic. Actually, in a real implementation, we also implement this idea. Actually, the number of recorded packets to be generated is determined on the fly. If that network has a lot of batch transmit, you may not generate this. You may not generate this. This is a more practical approach. Okay, we can have this different method to generate recoding approach. This is several approaches we introduced here. The next is number of recorded packets to generate. We have different approach to generate recorded packets, but how many recorded packets to generate? We use an optimization. We solve an optimization. We consider, we use LAN network as an example. This network has a length L. We fix the batch size M. Also, we fix the recording method we have talking about. We want to maximize. We use this expectation of pi L to denote the expected rank. This expected rank is involved the number of packets we generated for each batch. This is M tilde. We want to optimize not only this. As I mentioned that if you only optimize this value, it will be M. we will optimize expected rank over M tutor. Actually, M tutor can be regarded as the number of uses of the networks. It's our communication cost. But you can use other communication costs. Communication cost depends on your problem. But here I use this example. I use M tutor as my communication cost. This M tutor is the number of packets you transmit for each batch, right? So it's a reasonable communication cost. And R bar star is the optimal value of this expected rank over M tutor. Okay, I can do some calculation and get some results. This is the optimal value. This for field size, 2 to the power 8, the large field size. The value is slightly better than the case of our baseline. And now you see the case of smaller field. You see that even for binary field, for binary field, and the batch size is 1. This curve becomes flat when the network length increase. This is the same number for 1,000 hops. Up to 1,000 hops, you see that for the case of M equal to 64, field size is 2 to the power 8. We can still achieve this point. This is, I think this is about 0.65. Higher than 60% of this capacity. It's up to 1,000 hop already. The trend, you see that it's quite flat. Actually, it's like a 1 over log L trend. Okay, let's have a break. After come back from the break, I will tell you actually, this trend is true. It's 1 over log L. Okay, let's continue. We do have a lot to cover in the second part. Okay, just now we saw that the optimal value kind of decreasing in the order of 1 over log L. So this is good news, actually, for even thousands of hops is here. Actually, about 10,000 of hops, you will see that they only decrease a little bit. This is very good news. And the second is about the optimal M tutor. When the number of hops increase, we can calculate the number of the optimal M tutor. You will see that it increasing roughly logarithmically. For different batch size, different field size. Actually, for different field size, the curves are very close. 1,000 hop, similar trend. To understand this trend, we solve a toy case, M equal to 1. In this special case, we can derive that expected rank is of this formula. Epsilon is our loss rate. M to the power M tutor, totally 1 minus this to the power L. We maximize this. We can solve this optimal value not explicitly. Something we don't, we cannot get the exact value, but we know the order. The M tutor, the optimal optimizer is in this order, log L over log 1 over epsilon. And the optimal value, R star, is just another way around, log 1 over epsilon over log L. This justifies my conjecture. And another good news is that when this M tutor is optimal, my expected rank is in a range. We don't know exact value, but we know it's independent of epsilon. That's independent of the packet loss. Actually, no matter what is your packet loss, if you optimize your M tutor, in terms of this loss, it turned out your expected rank is independent that. This is good news for autocode design, actually. We will talking about that. The autocode design is covered, the packet loss that does not affect the autocode. But we haven't generated this calculation for M that is larger than 1. So that's I only say that it's a conjecture that they all follow this logarithm order. That's now the optimization. We assume that I know everything. I know the packet loss on all the network links. I collect them together to do the optimization. But the packet loss rate on different network links can be different. It's difficult to collect all the loss rate, especially when the network is very long, not practical. So we design a heuristic decentralized optimization approach. Each node only uses its local packet loss information. A node only uses its outgoing link and the incoming link, the loss information on these two links. Based on this local, and the objective to optimize is you can choose an objective to optimize. Yeah, this is a heuristic. You can choose to optimize the expected rank on the next hop, or you choose to optimize the expected rank at the destination without knowing the loss. But you can assume a certain loss, make an assumption. So there are many different heuristics. Yeah, I don't want to discuss this heuristic, but I want to show that this heuristic approach works well. I compare this R local is we obtain the optimal value based on this heuristic local optimization, and this R star is the optimal value. We do 500 instances where we assign the packet loss rate randomly on all the links. And we compare these results, compare this 1 minus this ratio. We found that they are all within 10%. Yeah, the difference is within 10%. They turn out to be very good. Yeah, you don't need to collect everything to a certain point to do the optimization. You do decentralized optimization using some heuristic idea. You get very close to the optimal value. This approach, we can further improve this, refine the number of recorded packets for different batch. Just now we're talking about for all the batches, we generate the same number of recorded packets. But you can do different. For a batch, of a rank that is higher, you receive a batch. If you see its rank is high, you should potentially generate more packets for this batch. For example, you get 2 batches. One is of rank 1, another is of rank 16. If you generate 16 packets for this batch of rank 1, you see a lot of redundancy, right? Yeah, so you should generate different packets for different batch. Yeah.
So M2 is always larger than the number of non-erased packets, right?
Non-erased packet. Right now, in this model it is. In land network it is, but
you have to optimize it every time.
Not necessary. Every time, not necessarily every time. But here I consider some static optimization. Yeah, you can do it. But in our math students at the bank, they will do a demonstration later. In their system, actually, this is generated on the fly. How many packets to generate? It depends on the flow. If you have very high incoming flow, you will not expect to generate many recorded packets that will conject the network. So the practical thing we have more to discuss, but here we want to illustrate the basic idea, how to optimize this. So for here the idea for different number of received packets of a batch, you may generate of different ranks, you may generate different number of recorded packets. It actually improves the performance, especially when the batch size is small. I will not go to these details. So just now I'm talking about how many recorded packets to generate. Now come to our third problem. The first is how to generate the recorded packet. The second, how many to generate. And the last, how to transmit. Right? How to transmit it depends on loss model. Just now we're talking about independent loss. We assume a loss rate, I generate independent loss in these calculations. If you do independent loss, you know the number of packets you received. These are, in our case, is the rank. It's a binomial form, right? It's an independent loss. It's like this curve. But in a real-world loss, we experience here, the loss pattern could be like this. Means that with certain probability, you receive very low rank. Sometimes you receive very high rank. But in independent loss, your rank is quite concentrated. Which is better, independent loss or this real-world loss? You see, real-world loss, we have a high rank batch, right? This seems to be not bad. Let me give you an example to explain why the practical case is worse than the independent loss. Consider M tilde is 20. That means we have 20 packets transmitted for a batch. We consider two loss patterns. The first is called the loss occurs evenly on all the batches. In this case, 4 packets are lost for each batch. You transmit 20, you lose 4, right? So eventually, 16 packets are received for each batch. This holds for all the nodes. So even at the destination nodes, you receive 16 packets for each batch. So this is a perfect case, right? So capacity 0.8 can be achieved. That means all the batches, suppose the original batch is 16. For every batch, you receive 16 packets. They are off rank. The second case is we lose a batch in a whole. That for 80% of our batches, no packet loss. And for 20% of the batches you transmitted, they are all erased. All the packets in the batch are erased. That means hop by hop, you will lose 20% of batches. Even though all the other batches you receive in whole. So the destination node receives only 0.8 to the power L fraction of all the batches. You will see that the throughput rate cannot be higher than this. This will tend to 0 exponentially. So this is the reason why I say this real-world loss, like this, is worse than the independent loss. Right? Even though you have higher chance to get batches of higher rank, but you have a higher chance to get batches of very low rank. That's very bad. To resolve this problem, we can use interleaving, because we want to have the loss occur on different batch evenly. So we can apply transmit the batch not one by one sequentially. We can interleave them. Suppose we have an interleaving block of L batches. The source node may apply a random permutation of these packets to transmit. The point I want to emphasize here is that we do not need to apply this. Interleaving will generate extra latency. But we do not need to apply this random permutation on all the following nodes. Because when you receive a permuted block, it's already permuted, interleaved, right? You just transmit in the same order you received them, and insert the recoded packet randomly. Yeah. So you do not generate latency hop by hop. So the interleaving does not introduce much latency. About batch transmission, we have talking about in LAN network. Now I will introduce how to apply the transmit batch over more general networks. We first look at general unicast network. We can solve the problem by identifying multiple paths from the source to destination nodes, and transmit our batch on these paths using the LAN network approach. So the LAN network approach can be generalized to general unicast network. But we do have the problem about how to select these paths in a heterogeneous setting. We also have the research issue about how to optimize the network node operations if there are multiple paths shared by go through one node. We do have some research issues here, but in general we know that we can apply the similar idea of LAN network. And the line network approach can also be generalized to tree networks, right? You have multicast, but if you network form the tree, it's easy to generalize the line network approach. But for general multicast, like butterfly network, you can now use tree packing. Packing a tree is not optimal. In butterfly network, we just mentioned that we kind of packing this. For each destination node, we found the 2 edge disjoint paths. This blue path, this brown path. We need to route our batches across these paths, but here, batches will meet together. Yeah, we need to do something special here. Let me show. We have 2 approaches. The first is that we transmit the same batch on different paths. Suppose we have a batch of size m. We separate it into 2 parts. Each part of m over 2 packets. Suppose m is even. And we transmit each part on one path. X1 is on this path, and X2 on this path to T1. Simultaneously, we transmit X1 on this path to T2 and X2 on this path to T2. But at this node, X1 and X2 met together. Then we apply network coding. Here, I didn't illustrate the batch transfer matrix here. During the transmission, we have batch transfer matrix. I don't illustrate the batch transfer matrix. So this addition, we have actually need to multiply a batch transfer matrix of on X1 and X2. We need that. We can do network coding here, then transmit this network coded packets to their destinations. This approach, we don't generate new batch, right? It's X1 and X2, they are supposed to be in the same batch. So follow our guideline of how to do recoding. The destination node just decode all the batches it received from different passes. But we do have several issues. You see, if we have 2 paths, we need to separate our M into 2 parts. If we have many batches, we will separate the batches into very small parts. But we don't hope the batch is very small after separation. So the batch size should increase with the number of paths. Another issue is that we need to synchronize the receiving of this X1 and X2 at C. If the paths have different latency, that is difficult to be achieved. Actually, in our practical networks, it's very difficult to synchronize 2 packets in a network transmission on different paths. If they are not synchronized, you cannot apply network coding, then the efficiency on this link will be low. This is practical issues. Now we have another idea to solve this problem. We can transmit different batches on different paths. This X and X prime, they are not the same batch. They are 2 different batches, each of size M. And similarly, we transmit them on very similar to before. But here, when these 2 batches meet at node C, we code them together. This is a very strange thing based on what we have discussed right now, because the recoding here generates a new batch. Because this is, we mix the packets of 2 different batches. We mentioned that we hope recoding only makes the packet of the same batch, but now we mix the packet of 2 different batches. We generate a new batch. The decoding will be an issue. But the nodes where different batches are recoded together are controllable. We know only node C generates new batches. All the node A, D, B, these other recoding nodes, they don't generate new batches. So only node C. There are several decoding strategies, but I would say that in general, we need more research in this part. We can do successive decoding of batches on different passes. For example, in this case, we can first decode the batches transmitted on this path to T1. Because these batches are generated at node S, no new batches. After decoding the message on this path, we can use the message on this path to cancel the X received in this packet. Then we will decode the packet, a clean batch of X prime on another path. This is successive cancellation. We can also use another approach that people have explored, that we can design degree distribution with recoding into consideration. That's because you may consider a new batch is generated, but it's a new batch with just the summation of the original degree of these two batches. This batch, you suppose its degree is basically the summation of x, degree of x prime. The degree distribution will be changed, but you know where the degree distribution will be changed. This is controllable. So it may be possible that you can design the degree distribution. Another idea is that this is successive decoding. When the successive decoding does not work, you need to jointly decode all the batches. This we have some works on this. It's called coupled codes. You can you couple two kind of code together inside networks. You can still decode them jointly. Okay, I will not go into the details, but this is in general we can apply BATched code on multicast, transmitted batches. Okay, we have finished the recoding part. In the recoding part, we discuss how to transmit a batch, generate recoding packets. The recoding eventually generate a rank distribution. This is the rank distribution will be used by the outer code. Now we go into the design of the outer code. We first start with the Ppd coding. In the Ppd coding, the design input, in addition to the batch size and the outer code field size Q, we have one or multiple rank distributions. And the design output will be a degree distribution. And we can also calculate the attributable rate of your design. Here, the purpose is to minimize this coding overhead. Remember that we want to make it as small as possible. The best is 0. Let's look at some details about how to solve a batch. We know this is the figure of the graph we want to use decoding a batch code. For each batch, we have an associated linear system of equations. We define a new notation, GH. The rank of GH is called our effective rank of batch I. A batch is decodable if and only if its degree is equal to its effective rank. Right? This degree equal to effective rank. It means that your number of variables is equal to the rank of your coefficient matrix. The degree of a batch will keep decreased during the BP decoding because some of input is erased. Suppose that a batch is decodable when its degree is reduced to S. S is an integer. If and only if S is equal to its effective rank at this moment. This matrix GS is a totally random matrix of S rows. Then I define a notation. This zeta RS as a probability that your effective rank is S when the batch transfer matrix has rank R. If you're curious what's the value of zeta, I'll give you two examples. When M is 1 and G is all 1 matrix, this zeta is 1, 1 is 1, 0, 0 is 1. But for our case of interest, when M is larger than or equal to 1, G is a totally random matrix, zeta is of this formula. I leave this as an exercise. You can see how to try to derive this. Yeah, we will not use directly of this formula. We only need to know zeta is this probability. Let's first see the asymptotic analysis of batch code. The setting is this. We have a batch size M, design rate theta, degree distribution psi, rank distribution h. We define a function involves both the degree distribution and the rank distribution. X is a value from 0 to 1, real number. Okay. The formula here, we will explain this formula later. This is D multiplied by psi D HR. This is a binomial term, and this is our zeta just defined. Our theorem is that the BP decoder recovers at least eta fraction of the input packets with a high probability if this function is larger than 0 for x from 0 to eta. So this is a sufficient condition such that our BP decoding can recover at least eta fraction of the input packets. You see, the eta can be very large. Cannot be 1. Yeah, eta cannot be 1, but it can be 0.99. Yeah, if you like. We will see what's the price you pay if you use larger eta. Let me check how many time I have. I may elaborate a little bit how to prove this. The idea actually is quite similar to the existing analysis of function code, so I will not go much into details. We can look at the first approach. Yeah, we can look at this random decoding graph. Look at the edges, instead of look at the nodes. We call this variable nodes and this check nodes. We see an edge is of degree D and effective rank R if it is connected to a check node of degree D and effective rank R. So suppose the rank of this, effective rank of this node is 2, then this edge is of degree 2 because its degree is 2, right? And effective rank 2. I say my time start at 0 and increase by 1 for each variable node removed. Because here I don't remove all the variable nodes together if this batch is decodable. I remove all these decodable variable nodes one by one. Yeah. Every time I increase time by 1. Then I use this EDRT as the number of edges in the decoding graph at time t with degree D and the effective rank R. So this is a random variable. I want to know how does it change with t. Its initial value, we know it will converge to this. Yeah, initial value. I will not elaborate. When D is larger than R, suppose that an edge, your degree tends to reduce because every time the degree is reduced by only one variable node is erased, your degree can be reduced by at most 1. If your degree is erased, your effective rank may be the same or reduced by 1. We know that the probability that your effective rank preserved to be the same if this probability, alpha dr. Yeah. And if you are here, in this position, your degree and rank, they are the same. These are the edges that correspond to decodable variables. Your degree decreases by 1, your rank must also decrease by 1. Yeah. We know that's how the evolution. But the exact density evolution is quite complicated because the edges are not independent. Some edges may connect to the same variable nodes, so they are not independent. So we calculate the expected changes over time. EDRT for t plus 1 minus EDRT. Yeah, the expected difference based on the conditional expectation based on the previous stages. We can obtain this formula. We particularly care about this is ERR. This is the case that degree equal to the rank. When degree equal to the rank, this means these edges are solvable. We hope that this E0, the number is non-zero, because once E0 becomes 0 at certain time t, your decoding stop. No decodable batches, the BP decoding stop. So we also calculate the expected change of E0. We get this formula. Yeah. The next step, this does not help much if we cannot get more, because we cannot solve this, this equation. We use an approach, a differential equation approach. We approximate this random variable by deterministic values. We substitute this EDRT by this n rho DRT over n. This is just a function. We don't know what is rho DRT over n right now. And we define tau as t over n, let theta be k over n, this is the rate we have designed. Then we let n tend to infinity. After doing these things, we obtain two, not only two, these differential equations, actually many of them. These are deterministic function, this rho. Then we can solve these differential equations and prove that this approximation actually is, this random variable actually converges to this. Yeah, we have the existing theory to guarantee that. After solving this differential equation, you will get the omega function I defined. Another approach to prove this may be using the tree analysis. This may be more intuitive. Yeah. We have a kind of tree. We expand our decoding graph, this bipartite graph, into a tree form. We do it in this way. We start with a variable node, then get its neighboring check node. Then from the check node, we get its neighboring variable nodes. Yeah. This is after 2 rounds, you get this tree of depth 1, 2, 3, right? Or 4, depth 4, tree of depth 4. When the graph is very large, this tree, not this tree, this subgraph with a high probability is a tree. So we can study the decoding performance on this tree. And we can get this iterative formula. Let XL be the probability that the root of a tree of head 2L minus 1 is recoverable by applying the BP decoding of BATched code. And we know Xi is of this formula. Xi is decodable only if one of its adjacent batch is decodable. Yeah, we can calculate this formula. And one of its adjacent batch is decodable is given by this. Now you see the term that I defined in the omega here. Yeah. So I will not elaborate here, but we can prove this theorem. Now we come back to the theorem, how to apply this theorem to show that, we haven't designed the degree distribution yet. We just tells you that for a given distribution, degree distribution, and the rank distribution, this is a sufficient condition that we can recover the eta fraction of input. We can, based on this sufficient condition, derive an optimization problem. We want to maximize the coding rate, theta, such that this condition is satisfied, and by choosing different degree distribution. Here, the rank distribution H is given, because the rank distribution is determined by the inner code. Inner code already tells us a rank distribution, then we use that to optimize the outer code rate. And this optimization will give us the optimizer is the desired degree distribution. The first results about this optimization is that we have a parameter d here. D is the largest degree you want to use. How large degree d you want to use? You know that if you want to you have a larger d, the optimal value of this is potentially larger. But we can show that using d that larger than this value does not give a better optimal value. That means your degree, you do not need to use degree larger than m over 1 minus eta. So this is a value that is dependent of the number of packets you transmitted. Then we let theta hat be the optimal value of this optimization. We know, of course, theta hat is upper bounded by the expected rank. This is a trivial upper bound. And we also know that when your rank of the expectation, the rank of the transfer matrix is a constant R. That means your transfer matrix always take rank R. We can derive that this theta hat is at least R zeta RR. And this value tends to R when Q tends to infinity. This means that actually the upper bound is achievable when the rank is a constant. If the upper bound is achievable, that means the coding overhead is 0. But in general, when this rank is not a constant, we don't know whether this is achievable or not, theoretically. But we do a lot of numerical results. We test this optimization. We use 4 to 10 to the power 4 rank distributions, randomly sampled. And we use different eta values. And we found that the ratio, this eta theta hat over the upper bound, is very close to 1. Very, very close to 1. For more than, if you look at here, for more than 98%, they are within, for more than 99%, they are higher than 0.98. This simulation tells us actually that the outer code can approach the rate very close to the upper bound. That means the coding overhead can be very, very small. This is asymptotic results. Now, how about, just now we're talking about one rank distribution, but we know BATched code can be used for multicast. And in multicast, you may observe different rank distributions by different rank distribution. Even for a single destination node, the empirical rank distribution may not always converge to the same value. We can solve this problem by 2 approaches. The first approach is that we design a better recoding approach so that our rank distribution always looks very similar. This is a recoding approach to solve this problem. We can also use the outer code approach to solve this problem, that by design a degree distribution that is simultaneously optimal may not be good. Yeah, we cannot say optimal. Good for multiple rank distributions. Yeah, I use this example to show it. Suppose we have 3 destination nodes, and they suffer from different packet loss rate. This is 0.1, this is 0.2, this is 0.3. And we got 3 rank distributions, H1, H2, H3. I evaluate the achievable rate for different rank distribution and different degree distributions. The first row is their expected rank. The second row, I use a degree distribution optimized for H1 individually, optimize the Phi1 for H1. So the triple rate for H1 is very good, but it's not very good for H2 and H3. And Phi2 is optimized for H2. You see it's not very good for H3, but it looks okay for H1. Phi3 is optimized for H3, And for H1, H2, it works, but not as good as the phi 1 for H1, right? Another interesting thing we can observe is that the degree distribution optimized for rank distribution with a higher loss rate can also be used for a node that with a lower loss rate. Because a node with a lower loss rate, you can always emulate a higher loss rate by artificially generate loss at yourself. We have another rank distribution, this we call psi fair. Because for this rank distribution, you see it is very good for H3. But for H1 and H2, it looks okay, but not much higher than this 10.81. But their expected rank is much higher. So can I have a degree distribution that for a rank distribution with higher expected rank, we can achieve higher rate? Yeah. So this fair, psi fair is designed in this way. You see that, it's higher than this value, it's higher than this value here, but it's slightly lower than this value. This is an example. Let's show how these results are obtained. In general, we can optimize a degree distribution for multicast by this way. Here, for this constraint, instead of consider a particular rank distribution, I consider a set of rank distributions. Solve the similar optimization problem. The optimal value, h theta, this edge, is upper bounded by the minimum value of the theta head edge. We optimize this, optimize the rate for individual rank, then we take the minimum. This gives us an upper bound. The equality here holds for the example here. This example holds because the minimum is the minimum of these three. The minimum of these three is this value. And this is the overall minimum attained by phi 3. Phi 3 actually attained the optimal value for this optimization. But in general, we cannot achieve the equality. One particular problem here is to solve this optimization. Sometimes this edge may have many rank distributions, may not even be countable. That makes this optimization difficult to solve. Yeah, we will need some approach to simplify the optimization. You need some tricks to do that. For example, I give an example here. We define a set of rank distributions B mu. B mu is all the rank distributions that can potentially support rate mu. That means the rank distribution with expected rank larger than or equal to mu. So this is a very large set of rank distribution. I want to solve the optimization with respect to this B mu. For different value of mu, we see that it's different compared with mu. For different batch size, we can calculate this. In general, there is a gap, right? This mu is our upper bound, there's a gap. But this curve tells us the guaranteed achievable rate for multicast. Because for B mu is the largest set of rank distribution that can potentially support rate mu. Practically, you can only have smaller, your rank distribution will be always a subset of certain mu. So this rate can be potentially higher, more close to mu. So this is a guaranteed rate for multicast, for BATched code. If you don't know what kind of rank distribution you have, you can look at these two curves. Use this approach to find the guaranteed rate for multicast. Just now we're talking about fairness. In addition to optimize the multicast, we can use this we call fair multicast. Here we optimize this ratio alpha. Alpha here. Alpha is the ratio of your expected rank that can be achieved. Here, if you have a higher expected rank, your attribute rate alpha, it's the same. So this overall ratio are the same. So your attribute rate is higher. And for the also we have an upper bound. And for the example we're talking about before, this upper bound can be very close to 1, not exactly 1. Again, we have the issue that how to solve this when H is very large. We know that fountain code is a universal code. It's BATched code a universal code. In general, it's not. But this, whether it's universal or not is depends on the set of rank distribution you're talking about. For a set of rank distributions, we can use this eta alpha hat h to evaluate its universality. If this value is very close to 1, it's more close to be universal. We calculate this also for this beta mu, this set of rank distributions. When mu becomes larger, it's very close to 1. This is universal code, but this set of rank distribution is very small. But when mu is close to 0, this includes all the rank distributions. You see that when mu is 0, we can find a rank distribution, a degree distribution that achieves at least 0.5 of your expected rank for any rank distribution. So this is another good news that you actually have a universally good degree distribution that works for any rank distribution, achieve at least half of the rate for m equal to 16. And for m is 32, the rate is slightly lower, like that. But in general, you don't expect all the rank distribution will happen. You will try to design the inner code to make the rank distribution in a small set. Okay, just now we talked about asymptotic analysis. We know asymptotically we can achieve coding overhead 0. But practical code are always of finite length. The degree distribution optimized for using the asymptotic analysis may not have a good performance. We will show that later. We have the numerical results. So we want to use this so-called finite length analysis to evaluate the exact decoding performance for finite block length, and then optimize the corresponding decoding performance for finite block length to design better degree distribution for finite block length. We can calculate the so-called stopping time of Ppd coding. The input is a BATched code with these parameters. And we have this RLNC is the number of decodable input packets at time t. This is random variable, number of decodable input packets at time t. If this becomes 0, the decoding stops. So the stopping time for a BATched code of n batches, the probability you stop at time t is that RNT is 0, but for all the previous time, you are not 0, right? We want to calculate the distribution of this, this distribution, stopping time. But we cannot directly derive a formula for RT only. We introduce another random variable, CNT. CNT is the number of undecodable batches at time t. We can derive a joint distribution of these two random variables using a recursive formula. It is not a kind of closed form, but iteratively we can calculate this distribution. We will not elaborate here. This is something that we can get. The finite length analysis is a recursive formula, but we can use it to derive some closed form results. For example, the BP decoding error exponents. We can get this closed form based on the finite length analysis. I will not elaborate here, but we can also get the expected number of batch consumed by BP decoding, because when the BP decoding stop, it's random. So the number of batch consumed is a random number, so we can calculate the expectation. In general, this is very difficult to calculate. It's an infinite sum. But using our analysis, we can derive a formula of a finite number of terms. But it's still difficult to calculate. There's so many terms. But using the finite length analysis, we can get better degree distributions. I compare 3 degree distributions in these 2 figures. The first is the one we optimized using the asymptotic approach. This is 5 BP. This is a asymptotic degree distribution. We're using the asymptotic approach, 5 ASY. This red one, 5 BP, is the one we optimized using the finite length approach. This axis is the error probability. You see, the error probability is much lower. Yeah, the red one is much lower than the green one. The blue curve, I get the degree distribution that has the highest error exponent. Eventually, this blue curve will be much lower than red one. But for the case that we are interested, it's not quite useful, because if you look at here, we know if we want to achieve coding overhead 0, n should be about 22. Yeah, but this error probability is always 1. So the usable error probability may be here for n equals to 30 or 35. For this right degree distribution, we can achieve error probability below 0.2. But this is not very good, right? Coding overhead looks still very large. But the reason is that this code is very short. We only have 256 input packets. So the question comes, can we do even better than this? If we want to achieve 0 coding overhead, but now if you want to have low error probability, you have to use n that is much larger than this value. So this is the next part about inactivation decoding. Actually, using this idea, we can achieve even almost 0 coding overhead for short block length. So after the BP decoding stops, what can we do? BP decoding stops when there is no decodable batches. We can do Gaussian elimination, but that has a high computation cost. We don't want to do that. The inactivation decoding is an approach that combines BP with Gaussian elimination. The idea is that this idea was also proposed by Sokolahi and Ruby. We can assign an undecoded input packet as decoded. They call this inactive. Just even though this input is not decodable, we assume it is decoded. Then we substitute it into the batches and resume the BP decoding. And we can do this multiple times. If you have another chance that you cannot BP decoding stops, then you inactive another packet. So eventually, you will solve the linear equations that all the input packets are either decoded or inactive. And these inactive packets will then be recovered by Gaussian elimination. I illustrate this by this figure. Suppose this is your linear system. your input variables, you don't know. You have this matrix and this output. Because this matrix, you see it's tau, so the linear combination, linear equations cannot recover all the input. So you try to solve this using inactivation, that you can inactive some packets here, 2 packets. You choose them as known packets. Then you solve the other packets. By Gaussian elimination, you get an identity matrix. But you didn't truly solve all the variables, because now you get this one. This one is mixed. Because these two, you don't really know it. But if all the linear equations you get, you have to stop here. But to finish the decoding, you need actually more linear equations. This coefficients and this output. You can substitute the first part to cancel out these parameters. You get this part, and these equations here, this becomes 0. This equations here is only about inactive symbols. Then you can solve the inactive symbols by Gaussian elimination, recover these 2 inactive symbols, then substitute them back to the other part. You will recover the whole system. So we will, the design of the batch code with inactivation decoding, we want to, we want to first reduce the number of inactive packets, because that is about how much packets we need to solve at the end by Gaussian elimination. We don't want to have a large number. To achieve this goal, we will use finite length analysis to study inactivation decoding, because inactivation decoding only applies for finite block length. For very, very long block lengths, we don't really need inactivation. Then we will optimize the degree distribution to minimize the expected number of inactive symbols. But it's not enough. We can further reduce the coding overhead by analyze the decoding linear systems, and also design better pre-code and batch code autocodes to reduce the coding overhead. We have used these 2 techniques. Let's go through them one by one. The first finite length analysis of inactivation decoding actually is very similar to the Ppd coding. Again, we get R is the number of decodable input packets at time t when using inactivation decoding. When do you need to inactivate a packet? When this number becomes 0, you need to inactivate a packet. So this is the probability that you need to inactivate a packet at time t. So the expected number of inactive packets is given by this formula. You just take the summation of this term for t from 0 to k minus 1. To derive this probability, you need another parameter c, this number of undecodable batches at time t using inactivation decoding. Again, we can derive this very similar recursive formula. The formula will be very similar, actually. I will not move on here. But based on this finite length analysis, we can design much better degree distribution. We have 3 degree distributions. The first one, the red one, is optimized using the finite length analysis. The second one is obtained using the asymptotic analysis. The third one is optimized for the kind of error exponent. We look at this curve. The optimal number of batch is about 22. You see that if you use n equals to 22, the expected number of inactive symbol is about 20. This is already very, very good, because totally you have 256 packets. You inactive 20 of them does not incur much higher computation cost. 20 is about our batch size. And we can do even better by introducing by study, look at this. We have talking about pre-code, right? We haven't discussed how to design this pre-code. Now we look at the pre-code design. Suppose we have K prime input package given by B prime, and K is the pre-coded input package generated by a systematic pre-coding. This can be given by the following parity check matrix. And the BATched code introduced the further linear combination, linear equations for B prime P, right? Overall, we have these are all the linear equations we have. We use all these linear equations to solve B prime, because B prime is our data. P is just some parity check value we don't care about. So we can cancel out P. Here J1, J2 is formed by this G tilde H. We can obtain a linear equation in a more compact form of this. B prime A equal to Y. Y is the received package. Now A is a matrix of this form. To solve your input package, actually, your whole matrix A have rank K prime. How to guarantee that or make that has a high probability? This is another point of view to design this inactivation decoding. We know the rank A is upper bound the rank by the rank of Z. Z is the combination of the J1, J2. We also know that if this W1, W2 inverse behaves like a totally random matrix, then as long as J has a rank higher than K prime, then rank A has rank K prime will be very high, 10 to 1. But we don't want to use totally random as a parity check matrix. That will be not efficient for encoding. So in general, we want to design this parity check matrix satisfy the 3 requirements. It can be efficiently solved during the encoding. This is encoding efficiency. And also about decoding efficiency, we want to, it is sparse so that we can decode the pre-code jointly with BATched code. Both encoding and decoding efficiency. Also, we hope it behaves like a totally random matrix. So we cannot just use LDPC. LDPC does not satisfy this requirement. So the idea, by Sokolahi and Ruby, is that we, in addition to LDPC, we introduce some high density parity check constraints. Okay, just now we're talking about the rank. If rank J is high, then how to guarantee rank J is high enough? A asymptotic analysis tells us that if your total rank is high enough, then the rank of Z will be at least eta K. This is asymptotic analysis of BATched code. We know that. But how to improve the rank Z for finite length? This is asymptotic analysis. For finite length, we want to increase the degrees of batch that will improve our rank of Z. But increasing the degree will destroy our degree distribution. So a better idea is here. We again can use their idea to use this so-called pre-inactivation. The input package, we separate the G tilde I into 2 parts. This A part has the same number of non-zero rows as GI tilde. And the GPI part has a small number of rows, same for all I. So the input correspond to G tilde IA, we call them active packets. They are encoded using a normal BATched code. The other input packets, we call them pre-inactive packets. They are introduced into the batches, but they are inactive from the beginning of the batch code decoding, so that they do not change the degree distribution, but they increase the real effective degree. So by using this idea, we can design very good batch code with short block lengths. Actually, you see that the coding overhead for short block length is very, very low. 1,600 is, the average is only two packets. Yeah, maximum is 16, many of them are 0. Yeah, this finishes the analysis part of batch code. We basically achieved our goal that we make the coding overhead almost 0. And we also roughly know how to optimize the rank distribution, the recoding in many scenarios, but not every scenario, of course. We do many experiments of batch code in the past several years. We have an open source batch code and decoding algorithm implementation you can find online. And we have test batch code on various hardwares, including various routers, some IoT devices like Raspberry Pi, and laptops. We also test batch code with different various communication protocols like this Wi-Fi, Zigbee, its commercial names. In addition to use batch code as a kind of library, you can, of course, programming to generate your implementation. We also try to make batch code as a communication protocol, works like TCP/IP. That will be very handy to use. You just use kind of our sockets to do the programming. You only need to worry about your application. We handle everything from the transport layer, network layer to link layer here. We use basically in the batch code protocol, outer code is in the transport layer. It guarantees end-to-end reliability. The network layer we use inner code because that's network coding. The self-linking part is that for wireless link, you don't really know who you are talking to. It's not like wireless networks. You plug in the socket by yourself. So we need a self-linking to generate a network like this. We have 4 computers, how to build these 3 links. Today we have a demo. My students at the bank, they bring 4 laptops. They exactly form a network like this using this self-linking protocol. Could they bring the computers here to show the demo? We have a very short demo. Yeah, we will finish on time. They are our undergraduate students, year 2 or year 3. So each computer, face to them. Each computers will have 2 Wi-Fi dongles plugged in to the USB interface. And for computer, they will, after this computer start up, they will automatically form a topology like this. One of the computer will be, but all the links are right now they use Wi-Fi. And one node will play a video, and the video will capture a video. The video will be played at the end node. Let's see whether it works.
A couple of minutes to set the system up.
Okay, they need a couple of minutes to set up the system. Okay, then I can, let me show another demonstration during this time. We have a video. This is another demonstration we did before. Oh, the video is now. Okay, you can see it. These are the Raspberry Pis. We are similar configuration. We plug into USB dongles, 10 of them. The first is a laptop, the last is a laptop. In this case, this is a setting. We play 2 streams of video. One use fountain codes, another use BATched code to compare the performance. This is the result. Yeah, this is the one we transmit using BATched code. This is the one we transmit using fountain code. Basically, in our protocol, we just set m equal to 1. It's become fountain code. So the video stopped here because using this protocol, you can now receive new, you can see something here, but you don't receive much packets because too many packet loss. This is real world packet loss. We don't artificially generate any packet loss here. Real world scenario. We try to find this is our kind of reading room in the campus of CUHK. Is it okay? Oh, you are still setting. Okay, then maybe we like Raymond Yeung to summarize the talk first.
Okay, thank you. Okay, it's me again. So I actually have shown this picture in the first part of this tutorial, and maybe I can elaborate a little bit more here. So in fact, we in Hong Kong, the government is very keen on building a smart city, and the smart pole is a very important part of smart city. And in fact, we have been talking to a lamppost company to design lampposts for this purpose, and the Hong Kong government has already shown interest in employing BATched code in the eventual deployment of smart lampposts. Okay, currently one of the as I mentioned, I mean the service providers are very keen on putting base stations on these lampposts. So, and one important consideration is how to connect these base stations to the line network. Okay? So one possibility is to use BATched code, and other than that, they are also interested in putting surveillance cameras on these lampposts for different purposes. And in order to get these video signals out, one proposal is to use 4G technologies. However, for current 4G technologies, the bandwidth, during the good times, you can easily get maybe 10, 15 megabits per second. But during the rush hours, and then a lot of people are using handsets, and the bandwidth will go down very drastically. This is not something very desirable at all. Okay, so BATched code is a possible technology that can solve this problem. And currently, we are looking into the possibility of installing an industrial-grade PC on these lampposts to do the computation for BATched code. That's one advantage of installing BATched code on these lampposts, because these lampposts, you don't have to worry about battery powers and things like that. Okay, and you also can put in a high power PC for doing the job. And another reason for the lamppost company to be very interested in putting in a PC for these lampposts is because there are already quite a number of functions on the lamppost that needs to be performed by PCs. For example, there's some data and analytic functions to be computed on the lamppost, and because a lot of data are being captured, they need to do a lot of video analytic and things like that. And after doing this, they may or may not transmit the data back to the data center. Now, so the situation is that currently a lot of each of these functions, they require a separate PC. So they are having a big headache because they need to install a PC for this purpose and install a PC for that purpose, which is not something very good to do. And eventually, I believe that all of these things would be consolidated into the framework of fog computing or edge computing. Some of you may have heard about this. And in my opinion, fog computing and edge computing will be converging to something in common eventually. And so each of these boxes will eventually be a fog node, and BATched code, for example, will be offered as a microservice on a fog computing node. Eventually it will converge to this kind of situation, in my opinion. So another thing that I would like to talk about is this south-north water transfer project, okay, which is it's an ongoing project in mainland China, which part of it is already done, okay? So the idea is that the part that is being done, to my knowledge, is that so because the underground water in Beijing and Tianjin are kind of polluted and they are not suitable for drinking, so what they have done is that they've identified a lake in the south, and which is 1,400 kilometers away from either Beijing or Tianjin, I forgot which one, and with they built a canal all the way from the south to the north to move the water to the north, and the distance, as I mentioned, is 1,400 kilometers, but they take advantage of the height difference from the starting point to the end point. Okay? The height difference is only 100 meters, so the slope is really, really gentle. But they managed to build a canal all the way from the starting point to these two cities. Okay? And so whenever there's it passes through a valley, they have to build a bridge. Whenever it has to go through a hill, they build a tunnel. Okay? So along this very large canal, a very long canal, they have a surveillance system to ensure that the water quality is suitable to be consumed by human beings and things like that. And so it is actually a very large sensor network. And along the canal, they have already built they already have built a fiber network. But to what I have learned, some of these fiber networks are already damaged. I don't know exactly what's the reason. Maybe when it passes through some rural areas, some farmers just dig up the fibers. I don't know exactly what happened. And so at this point, they have plans to employ BATched code to replace the fiber system. And I believe for one reason, because BATched code uses a wireless system, it is easier to maintain, in some sense easier to maintain than optical fiber system. So we have been working with one of the units in the Chinese Academy of Sciences in Shanghai for that purpose. So I just want to mention to you that there's some real applications of BATched code ongoing, and perhaps in a year or two we can report more on that. Okay. So is the demo ready?
Yes.
I can pass this mic to you.
Yes, music. the BATched protocol. We mentioned this in different layer. We have the design. So to generate this video application, we only need to use Python to write some codes to capture the video and playback. So it becomes quite simple. But still now there are a lot of issues we need to solve. Last night they were debugging. So that's right now it's not ready for you to use, but hopefully in the near future maybe we can release some protocol for people to try out. This is a summary of this tutorial. We know that BATched code satisfied all the requirements we hope for a practical solution in terms of communication rate, computation complexity, storage requirement at relay, also end-to-end delay. The video delay actually is most of the delay is generated by the video capture, not our transmission. We solved the long-standing problem of packet loss accumulation in multiple hop wireless networks. Actually, converts a multiple hop network into a single hop wireless network. So you have a lot of loss in each hop, but end-to-end it looks like just one hop. So this is an enabling communication technology for various mass networks, IoT for computing and beyond. So we believe that this BATched protocol can make TCP/IP legacy. This is a more general communication protocol. It degraded to TCP/IP if we don't use the recoding. So this is very powerful in the future, I think. But we still, again, we need a lot of effort. We're talking about something here, but for example, we don't talking about how to do congestion control in the network coding scenario. That will be very, very, very important if you want to deploy this in large-scale networks. There are many applications we haven't talking about here. For example, in software-defined wide area networks, in content distribution, so on and so forth. So if people are really interested, we can contact to see, to do some research together. Thank you very much.